In this lecture, we're going to be looking at something called closed loop stability. We've kind of looked at that already in a number of different scenarios, but here we're going to be looking at it in terms of frequency domain type stuff. So we can see here we have omega going on here. All right. So suppose we have this fundamental control problem. This is our control loop that we may be working with. In general, we have a plant that we're working with. The plant takes input U, provides output Y. That output then gets measured, and in the process of getting measured, there's a noise that's added to the system. We use that for feedback, and we compare it with a reference signal. So a reference signal, this is the thing, we would like our output Y to follow this signal. And so that's a tracking problem. And so we compare these two. The difference is the error signal that we put into a controller. The controller generates our control signal, and we may not want that as an output. We may want to look at that. In addition, our system has D that enters. So not just U enters the system, but D enters the system. D is a disturbance that enters the system. And so in addition to a control signal, we also have a disturbance signal that's entering. So our overall system has a number of inputs, R, D, and N, and it has a couple of outputs, Y and U, that we may look at. So it's very common, for example, for the reference input to be fairly low frequency content. In other words, we don't expect our system to jump through. So R is the signal that says this is how we want you to jump through a hoop. We don't make R so high frequency content, that is changing quickly. We're not expecting it to change quickly, and so we're not expecting Y to change quickly. And so generally speaking, we're going to think of the reference input as being low frequency content. The disturbance input we're also going to think of as being of low frequency content. It could have high frequency content, but generally we're going to be thinking of in terms of low frequency content. That's kind of typical. So for example, if our system is a cruise control in an automobile, our plant then wants to follow the desired reference speed. Okay, so our output, we want the speed of the system to follow that reference. But our system may have this disturbance that enters. The disturbance could be, for example, wind resistance, or the disturbance could be the slope of the road that you're on. Okay, and so the slope of the road is not going, in general, when you're using cruise control, you're generally not on a very rough road, that's doing a lot of crazy things. And so in that case, for example, the road is not going to change very quickly in terms of how the force, and so that's why we think of it as low frequency content. So that's a typical kind of example. That's not the only possible example. Sensor noise. Sensor noise generally we can consider to have high frequency content. So this is a typical kind of single input, single output fundamental control problem. I say single input, single output. We could actually extend this to multi-input, multi-output as well. So first we're going to look at single input, single output loop shaping. Then we're going to talk a little bit about frequency weighting and multi-input, multi-output loop shaping. And then we're going to talk about open loop and closed loop performances and so forth. So here we're going to talk about these in future videos. In this lecture, we're going to look at these topics. Okay, so suppose we've closed our loop and we have a transfer function from R to Y. For now, we're ignoring the sensor noise, we're ignoring the disturbance, and we just have the reference input that's coming in. We desire Y to closely follow R. What do we need of this transfer function in order for that to happen? In general, again, the input signal R is restricted to a prescribed set. For example, we might consider only a step input or a sinusoid, We might consider the signal to be band limited, a band limited signal, and so we generally restrict R to be of some prescribed set. The closed loop system, which is also a function of the controller, must have near unit gain at all the frequencies of R. Okay, so if R, for example, is a sinusoid, then the frequency at that sinusoid, the transfer function magnitude at that sinusoid must be 1 in order for the output Y to follow the input R. If it's a step input, which is a constant, that means at DC, our transfer function has to have unit gain. At DC, when j omega is equal to 0, this transfer function needs to have gain of 1. So in general, we have to have near unit gain at all the frequencies of R. So for whatever frequencies these are. It's a little more difficult when you describe something in a band limited term. That means you need to have, over the entire band, you need to have unit gain. Okay, so this is the tracking problem. So in a graphical form, we can think of it this way. If the frequency content of R, if this is the transfer function response of our system, then the frequency content of R should be in this band, which is often referred to as the pass band. And we want our system actually to have a nice roll-off so that we have the transfer function is very small in the stop band. Okay. So let's look at some fast facts about transfer functions. In this case, we're looking at single input, single output, but again, some of this can be extended to multi-input, multi-output. For perfect tracking, both conditions must be satisfied. The magnitude of the transfer function must be 1, and the phase of the transfer function must be 0 at all the frequencies of the reference signal. Okay, at all the frequencies of the reference signal. So if we're looking at a band, like a band limited signal, so we actually have a band of frequencies that we're considering, it turns out that in the pass band, the transfer function magnitude cannot be perfectly flat. Cannot be perfectly flat. Cannot be exactly 1 for all frequencies in that pass band. So in order to get perfect tracking, in general, if we're looking at a band limited signal, we will not get perfect tracking because we cannot get exactly equal to 1. But we can get close. That is, if we have a small deviation, small variations, or what is often referred to as ripple, if we have small ripple in the pass band, then that may be okay. So in the pass band, the transfer function cannot be completely flat. So what does this mean? Well, if we look at the closed loop transfer function, this is actually the closed loop transfer function. Okay, so for this to have magnitude 1, okay, that means P of k and j omega. Notice that these are the same terms. If these terms are large, then this term will dominate 1, and this ratio will be approximately 1. Okay, and they will be equal to 1 exactly whenever pk is infinite. Okay, so that is something that we need to take into account. So in the pass band, the transfer function can be almost flat. That is, it can have a little bit of ripple in it, maybe a very small ripple. In general, we want high frequency roll-off to help filter sensor noises. Remember, we considered sensor noises to be high frequency. High frequency roll-off also requires the phase to change in the pass band. Generally speaking, that will require that. The phase change corresponds to a time delay of the output with respect to the input. So in other words, we saw this. We might have magnitude almost equal to 1 in the pass band, but we have not seen what happens to the phase. So the phase, it turns out, will change, and the faster it rolls off from being flat to rolling off, the faster it rolls off, the more this phase will change in the passband. Okay, so even though the magnitude may be 1, the phase is not 1, which means there's a time delay corresponding in the output. So in terms of loop shaping, we've talked about the kinds of things that are needed in the loop for the system to work properly. So in general, we have this closed loop system, or this is a general closed loop system. We generally want closed loop stability, so regardless of what kind of inputs we have. In general, we want large gains wherever R and D have frequency content, and we want small gain wherever N has frequency content. So if R and D are low frequency signals, then we want large gain there, and we want small gain wherever the noise has frequency content, which may be high frequency, which it seems like it's possible. I'm going to define two functions. Well, first of all, the function called the sensitivity function. So here's the sensitivity function of the closed loop transfer function. So remember, the closed loop transfer function has this transfer function form. If I take the partial derivative of this with respect to k and divide it by that transfer function, this is the function I get. So that's why it's called the sensitivity function. Anyway, I get this quantity, and notice I have an inverse. So I've written here in matrix form because even though I'm calling this single input, single output, we're going to see this extends to multi-input, multi-output. So the sensitivity function is like 1 over 1 plus pk. And so if you have 1 over 1 plus pk, this will, when this quantity is large, then this overall quantity will be small. Our sensitivity will be small. And so the reason we use the sensitivity function is that's another reason is that it is the transfer function from the disturbance input to the output of the system. Okay, so when we look at this diagram, the transfer function from this input to this output for the disturbance, this disturbance then is has that sensitivity function. That's the transfer function. So when D has significant values, that is at low frequencies, we want the sensitivity function to also be small. We can also go through and show that in this closed loop, E, the transfer function from R to E, from the R to the tracking error, is the same. It also has the same transfer function. It's a sensitivity function. And so we also want the sensitivity function to be small where R is not small. So we've defined the sensitivity function. We can define the complementary sensitivity function by this expression. So the complementary sensitivity function is actually the closed loop transfer function. That is, it's the transfer function from R to Y. But it's also the transfer function from N to Y. Okay. So generally, again, we've shown this, that when this quantity is small, then the sensitivity function will also be small. Okay, so for this, in this case, that means my system is not sensitive to the noise, which is good. However, we don't want R to be acting in that same way, those same frequencies, because otherwise it will attenuate the reference signal and it won't work very well. So complementary sensitivity function is called it complementary because the sensitivity function plus the complementary sensitivity function is equal to 1 for all frequencies. So the sum of these two is equal to 1. So if this is small at low frequencies, this will be almost 1 at low frequencies. if this is large at high frequency, or this is 1 at high frequencies, this will be almost 0 at high frequencies. But in any case, these two will always add up to 1 for all frequencies. And so in summary, in terms of loop shaping, given a plant, we would want to choose a compensator, controller K, such that this quantity is large at low frequencies. This quantity rolls off at to low values at high frequencies. So large at low frequencies, small at high frequencies. So in general, that's what we want. We can also talk about a shaping filter. Suppose that our disturbance has a frequency response that looks like this. We would choose a weighting function, W, such that W is greater than or equal to D for all frequencies. Okay, so that's the weighting function. It can be equal. Okay, so at low frequencies it can be equal, and then at high frequencies, again, because it's a disturbance, we don't exactly know what it will be, what its frequency response will be. And so what the W allows us to do is it allows us to consider a number of different Ds, and we'll actually come back and see this later in some cases. It allows us to evaluate a number of different Ds and use the same weighting function. So if we were to treat D this way, I have some finite energy or finite power signal V that enters a filter of frequency response W, and that gives us our disturbance. In other words, our disturbance can be generated this way. So in general, we will often look at the power of V being less than or equal to 1, or the energy in V being less than or equal to 1. And so in terms of our signal, and for now we're ignoring the reference input, we're only looking at the disturbance. We're also not having the noise. We're not looking at that right now. We're just looking at this loop. So with this loop then, we can go through and show that the power of Y can be shown to be less than or equal to something times the power of V, the input. And that something is this transfer function. So notice it includes the W. It also includes the K. All right. So if we have the power, if V is a power signal, then we have this inequality. If V is an energy signal, that is finite energy, then we have this energy inequality. And notice we have the infinity norm of this transfer function, which is the maximum magnitude over all frequencies of this transfer function. Okay, so we have that. Notice it's the same norm in both cases, whether it's a power signal or an energy signal. So what we would do then is we would look for when the product of the magnitudes of the sensitivity function and the weighting function, when that product is less than or equal to some constant gamma. Or another way of saying it is the transfer function the sensitivity function Bodie plot lies below this Bodie plot. Okay, so if this is true for all frequencies, that means this Bodie plot magnitude lies below this Bodie plot for all frequencies. And so that's how we would evaluate this. Okay, so again, if for good tracking, we want the sensitivity function to be small at low frequencies. So that's why we would have it this way. So if 1 over omega has this Bodie plot, then omega itself is going to have this Bodie plot. Okay, it's going to be flipped. Okay, so this tells us something about what. So again, W describes the frequency response of the disturbance, and so we can see that here a high pass characteristic corresponds to a low pass characteristic. Okay, so that's the weighted sensitivity condition that we have. So again, we're waving our hands a lot here. We're not looking at actual transfer function and numbers, but this is the basic idea behind these kinds of things. So, as I've said, some of the things that we've talked about apply not just to single input, single output systems, but to multi-input, multi-output systems. But in order to do that, we have to kind of look at this a little bit differently, because multi-input, multi-output is not just a single number. We actually have a matrix, and so instead of looking at absolute values, we have to look at norms or singular values. And so in terms of singular values, we have these relationships. The singular value, the maximum singular value of a product is less than or equal to the product of the maximum singular values. And if the maximum singular value of a product is less than or equal to 1, and D is not 0 indeterminate, then we can show the maximum singular value of C is less than 1 over the maximum singular value, 1 over the minimum singular value of D. So we have these two facts. So here's a product, and here is a just an inequality by itself between two matrices. So if we look at this quantity, we can go through and show that the maximum singular value of this quantity must be less than or equal to the minimum or the singular this ratio. So this is like what we had in the single input, single output case, but now we're working with singular values instead of absolute values in working with all this stuff. But it's the same kind of thing we're looking at. So in other words, in terms of frequency responses, this quantity, even though I have a sigma max here, largest singular value, this largest singular value is a function of j omega. So we can actually look at the Bode plot of this quantity. We can look at the Bode plot of this quantity, and we need to have basically this quantity be above this quantity. Okay, so all of this still holds, and so again, we would want to find a k for, so in terms of a design process, given a p, we would want to find a k such that this inequality is satisfied, where w is given by the disturbance. And if it is satisfied, then our system will have disturbance attenuation and so forth. Okay, so now again, we not only want k to satisfy this inequality, but we also want k to stabilize the system. So that's also another. So k has its handful in terms of what it needs to accomplish. So, but that is multi-input, multi-output loop shaping. And we'll come back and look at how this plays in a number of different situations. So this is loop shaping.